Okay, let's get this show on the road. Hello, everyone. Hope you're well. Welcome to another edition of Math 1207. Hopefully you guys have been good. Let's actually jump into it. Let me share my screen. Boom. Get everything set up here. And okay, and we're a go. So hopefully you can see the screen right now, and we're going to be talking about, it's actually something your textbook covers in section 7.5. I will be expanding on what your textbook tells you though. So I think it's actually a pretty good thing to go through. We're going to be talking about integration strategies. So we've covered a lot of integration techniques, I want to say about 8 at this point. And I just want to make sure that we can go through them and we can know when to use which strategy, how to mix and match strategies, what should go through your head when you see this weird integral and you want to figure out how to compute it. So that's what the first part of today's lecture is going to be about. So we've been learning a lot of things, and just so that, just to have like kind of a clear-cut way of how to do things in our head when we are going through an integration problem is what we are going to deal with. So that is today's lecture. We are going to talk about strategy when approaching integrals, because as you guys have probably noticed, integration isn't as straightforward as differentiation, right? Like back in Calc 1, it was obvious when you had to use the product rule or the quotient rule or the chain rule or something like that. With integration, you can have an integral and it's like, it's not obvious at all how you should go about doing it. So yeah, want to make that a little bit easier today. And of course, in general, it's not going to be easy across the board, but at least for Calculus 2, the kind of integrals I would expect you to be able to do, the approach I'm going to do here is going to be super helpful, at least I believe so. So you see a random integral. How do you actually go about computing it? How do you evaluate it? How do you solve it, etc.? And the first 3 steps you already know. We've been actually talking about this for a while. So step 1 is basically just try to apply a basic rule. So basic rule is just the list of rules that you should have memorized, you should know off the top of your head, and you should just actually know what these guys are. So for example, basic rules would be like, example, the integral of x to the n dx when your n is not equal to -1, or the integral of 1 over x dx. Or the integral of, say, secant squared theta d theta, right? These are all guys that you should know what the answers are. So this one is x to the n plus 1 over n plus 1 plus c. This one is ln of x, absolute values x plus c. This one would just be tangent theta plus c. So there are some, like the moment you look at it, you should already have an answer popping into your head. These guys are the basic rules, basically the guys that you're supposed to have memorized. I gave you a list of integrals to memorize. Wow, it's a few lectures ago. But I did give you a table, and I added a few more to that list in going through some of these techniques. But yeah, basic rules. The next step is to, okay, if a basic rule doesn't apply right away, and in Calculus 2, most of the time it won't, but you never know. Try to simplify it so that you can get a basic rule. So for example, if you see this integral here, 3x squared minus 2x plus 4 all over x squared, it doesn't really look like a basic rule. However, you can algebraically simplify this so that it looks like a basic rule, or a sum of basic rules pretty easily just by dividing dividing the denominator into each term. So you can have just the integral here of 3 minus 2 over x plus 4x to the minus 2. And now basically you already know that hopefully you remember the properties of integrals, that the integral of a sum is just the sum of the integrals. So you can actually think of this as 3 dx minus 2 times, and you can factor out constants out of integrals. So you have all these guys, and each of these are basic rules. So the power rule works on the first one. You get 3x. The ln rule, which I mentioned before, works on the second one. And the power rule works on the last one. So you add 1 to the power, and divide by the new power. So that will give you -4/x plus c, right? So either it's a basic rule or you can sort of simplify it to look like a basic rule, but those are the first two things that should go through your head when seeing any integral. What is the third thing? Substitution. Substitution is always the third thing. Now, it is something worthy of note that in Calculus 2 and beyond, substitution is less obvious than the substitution that you would have to do in, say, a Calc 1 class. So substitution was a technique that you learned towards the end of Calc 1. And whenever you had to do a substitution there, it was more or less obvious because whatever you had to substitute, you'll see its derivative somewhere else lingering in the function. It might be off by a constant factor, but that didn't matter. You could always divide that constant out. But it was clear that, okay, if my u is this, I can see my du part over there, right? This is no longer the case. It's not always going to be obvious when the du is present, right? Sometimes it can be hidden. Sometimes you have to multiply and divide by something to get it there or whatever. However, so that being said, substitution is supposed to be one of the things you think third, regardless of whether or not you see like the derivative of the thing you'd want to substitute present. So something like e to the square root of x dx, right? Something like that. You don't really see any u versus du present there, at least not visibly. But the correct technique to actually approach this one with is substitution. So the idea would be, when you look at an integral like that, the first thing you would try to think about, well, does that look like a basic rule? And the answer is no. But then you start to think, well, I mean, it's kind of like almost a basic rule. If only I didn't have that square root in the numerator, right? So you can look at this and you can say, well, it reminds me of the rule that talks about this, e to the x dx, but we have a square root x instead of x. So set u equals the square root of x might be something that you would think, right? So I know how to deal with it if I have e to a single variable. However, here I have e to the square root of some variable. You know what? Let's just call that square root a single variable because I know how to deal with that case, right? And then you sort of worry about where your du is going to come from after the fact. So you would, after making that, okay, so u equals the square root of x. Then you can start to do things like, well, u squared equals x, 2u du is going to be your dx. And now you can kind of swap that out. So now the integral becomes, well, 2 times integral of u e to the u du. And of course, you'd continue this by parts, but putting in the substitution makes it clear how you'd approach at this point. It's clear, hopefully it's clear. Int by parts is how you continue. Right? So you might see something like e to the square root of x, and you might be thinking, oh, that's weird. However, with a substitution, it clearly puts you on the right track. It makes it look a little bit nicer. E to the square root of some variable is weird. E to just a single variable is nicer. The du appears just by me working around the substitution. So I force, when I do the substitution, I force myself into a corner that I have to figure out what the dx is going to behave like. And that brings me to another situation that it should sort of be clear how to proceed. Same thing here. You'd realize that what makes this complicated, the 1 minus x squared in denominator makes this complicated. Complicated has a very specific definition here. Complicated means does not look like a basic rule. Right? That's how I'm defining simple and complicated in this context. Something is simple if it looks like a basic rule. You don't really have to do anything. It's complicated if you can't. It doesn't look like a simple rule. Does not look like a basic rule. Okay. So because of the sum, you realize that, well, if it was just a single variable under the radical, it wouldn't be so bad. I can do something like just divide the thing into the term in the top. So having the sum in the denominator is what makes it complicated. And so what you would do is you would think of a substitution, let u be the denominator. Right? Or better, as we've seen by now, u squared equals the denominator, so that I can even simplify it further. And so at this point, you would get u du is equal to minus x dx, and you would be able to say that and then you'd be able to say that, well, my x squared is going to be 1 minus u squared. And so when you go here, you'd realize that this part here, the x cubed, is going to be an x squared times an x, and I can deal with the x dx. And so this pretty much becomes now, say, minus the integral of 1 minus u squared over u times u du. And then these guys cancel. And so now you realize that your integral looks like a basic rule. In fact, it's the sum of some power rules, and you can continue there, right? You see something like this. Again, what makes this complicated? So what you can do is u equals the 1 plus x squared, or better, because now we're a little bit grown up, or better, u squared equals the 1 plus x squared. You would get your u du is equal to x dx. Then you can realize that here you would multiply by an x over x. Put it in here. And so that would give you a u in the top. You would end up with a u squared minus 1 in the bottom, and you'd end up with a u du here. Then you'd end up with a u squared over u squared minus 1 du. And at that point, hopefully it's clear that you should sort of proceed in sort of a partial fractions manner. You can subtract 1 and add 1. And so this will give you the integral of 1 plus 1 over u squared minus 1 du. And you can remember that that is the inverse hyperbolic tangent, or you can actually do something like a u minus 1 times a u plus 1 du, right? And that would be, well, a half minus a half. And so u plus 1 plus c, right? So we've seen integrals like that before. So, I mean, I'm rushing through this, but substitution is basically something that we've done since Calc 1. So I'm kind of rushing through the substitution. But you kind of see the idea here. You sort of see these integrals here. They're really weird. They don't look like basic rules. You also can't really simplify them to look like a basic rule because there's nothing really to do. And so what you'd always think third is, can I get a substitution to work? And basically your guiding principle would be, well, what's making this complicated? And if I replace that thing by a single variable, what are the consequences of that substitution? And can I squeeze in a dx somewhere, right? And so you kind of figure that out. Sometimes this doesn't actually work out, and you would see situations like that. So for example, in the middle one here, the x cubed over the square root of 1 minus x squared, if it were an x squared on the top, you'd realize that this sort of maneuver would not have worked out in your favor.
Professor?
Yes.
For the bottom, I know that the 1 over u squared minus 1 is the inverse tan, but when you do the 1/2 ln u minus 1, on the quiz, there was like a similar answer like that, and then they divided the ln's. Is that like just a simplification thing?
Yeah.
Okay.
Because ln of a minus ln of b is ln of a over b.
Okay, so this would be like u minus 1 over u plus 1 inside the absolute values technically?
Yeah, you could simplify this as a half times ln of u minus 1 over u plus 1.
Gotcha.
Yes.
Okay, thank you.
And those would be equivalent. And if you're typing it up, that would probably be preferable because you don't have, it's less space to type. Yeah. So, and this is the disclaimer, and this is something that we've already known. And I mean, I spend a long time harping on this again, but it's really an important idea, I think, is that the above 3 steps, you always do them in that order, right? You always first look, is it a basic rule? Can I simplify it to look like a basic rule? Would a substitution work? What would I substitute? What is making this thing complicated that I can replace with a single variable, right? These are, it's always the first thing that you kind of do, right? Always in that order, in fact, right? Because you really don't want to work harder than you have to, right? There are times when multiple strategies could work, but one is just harder to pull off than the other one. Like if a substitution or a basic rule or a simplification to a basic rule is going to work, it not only will it work, but it will be among the simplest things to get to work. And so you do want to do these things in that order, right? Now, beyond that point is where it starts to get a little bit more nuanced. So right here, you'll notice here I have the step 4, the 4's in quotes, because it's not really technically the 4th thing exactly that you would think. You always would think the first 3 things in the order that I gave you, but beyond that, you don't really think in a certain order. You basically would notice a certain technique would apply based on what is actually present in the actual integral. So the numbering that I have here is just basically numbered in the order in which I taught the technique, but it's not necessarily the order of priority. So that being said, let's actually move on to the thing that we learned right after substitution, integration by parts. Okay, so when would you think integration by parts is the question? Well, there are a couple scenarios in which you would think integration by parts, right? One is if you have a product of 2 different types of functions. So you'll notice that, for example, in the first example I have here, e to the x, that's an exponential type of function, while the sine x is a trig type of function. Or here, this is a polynomial or an A or P, depending on whether you memorized it as Lipit or Liate, or P, versus e to the x here is an E. So I have 2 different kinds of functions multiplying each other, right? So whenever you see something like that, integration by parts would probably be what you would think. Now, that again has some nuance to it, because not always would you do this. For example, in this situation here, I have an A and I have a trig function, but substitution would be better. So this is an integral here. The non-example that I have here is a kind of example where a student who looks at that and just without thinking rushes into integration by parts will actually have a hard time, especially if they split that integral into x cubed and the sine of x to the 4th, because sine of x to the 4th does not have an antiderivative actually, right? The antiderivative doesn't exist. Like you can't actually write it down as a function. And so a student who is approaching this with integration by parts will likely make the u the x cubed and the dv the sine of x to the 4th, and they would literally be in an impossible situation, but a lot of students would actually not realize that this is an impossible situation, and they sort of make up an answer for the integral of sine of x 4th, and it just doesn't work. And this would be a classic case of rushing into a more sophisticated technique without going through the previous 3 checks that I gave you. You see, when you see the integral x cubed times sine of x to the 4th, you're not supposed to immediately jump to integration by parts just because I see 2 different types of functions. You always go through the first 3 steps first. Is it a basic rule? Can I simplify to be a basic rule? Can a substitution work? You should already see that if I made u equals x to the 4th, my du is going to be an x cubed, and it's right there. This is a prime candidate for substitution, not integration by parts. So yeah, and I did mention this here in red. The following steps are not in any particular order, but you only apply them if the above don't work, right? So I'm assuming that everything after this point, you've actually tried to do a substitution. You've tried to apply a basic rule. You've tried to simplify before. And then you're in a situation where none of that worked. Then if you see two different types of functions, you can think integration by parts, right? Another situation, and again, assuming that steps 1 through 3 didn't work, another situation in which integration by parts is going to be useful is if you're looking at a function and there might just be one function, there could be a couple, but there might just be one function where you realize, you know what? It would be nicer to have its derivative present than it is to have the function itself, right? So if you see the integral of inverse tangent and you're like, you know what? I don't know how to integrate the inverse tangent. However, the derivative of the inverse tangent is 1 over 1 plus x squared, and somehow that feels more manageable to me. So this would be a prime candidate. You'll notice here that the derivative of the tan inverse is 1 over 1 plus x squared. And this guy seems more manageable in an integral. Manageable. Right? It's a rational function, so you automatically have things like where you think about like maybe a partial fractions because the dv is going to put something in there that maybe turns into a nice thing. So it's nicer to have the derivative, right? So once you actually do the u equals the tan inverse and your dv equals, well, dx in this case, you'd realize that your du is going to be 1 over 1 plus x squared, and your v is going to be x, and then you would end up with your I being u times v minus the integral of v du. And this integral here is nice by substitution. Right, that's a prime candidate for substitution. That's going to be 1/2 ln of 1 plus x squared, right? And it's good enough with substitution where you can almost do it in your head, right? So that's nice. Okay. Same thing with secant cubed, right? Same thing with secant cubed. You'd realize that yeah, you could break this up into secant squared and secant. And integral of this is nice. And the derivative of this would be nicer. And so again, integration by parts would be something that I would use to attack this integral here, right? Which we've seen the derivation of the integral of secant cubed. So you kind of know how to continue from here. But that's how you'd sort of start to break things down. It's either two different classes of functions, or I have a same classes of functions, or one function where it's nicer to work with the derivative than it would be to work with the original function. So that's another prime candidate. Of course, there are times when it would seem like this technique would work, but it actually won't. So this one here actually has no antiderivative. So it doesn't matter what technique you hit this one with, you're not going to get anywhere. We're actually going to see a way to find an integral of this thing, but it's not going to be in quote unquote closed form, but we'll get to that in phase 3 of the course. Is it phase 3 or phase 2? One of them. In the next phase, we'll actually see how to deal with this a little bit nicer. This one here, if you do int by parts, it leads to some sort of situation where you actually cancel out the integral on both sides. You end up with a 0 equals 0 kind of situation, which is not very helpful. It's actually one of the situations where it's nicer to use a simplification. The trick here is something called the product to sum formulas. Now, I won't expect you to actually know this in this course, so it's not you won't have to worry about this, but I decided that I'll just take a couple minutes and actually show you what I'm talking about, because in higher level courses, this might be something that someone would just expect you to know. So for those of you who have to take differential equations eventually, you're going to get into a situation where you're doing things called Fourier series and Fourier transforms, and you're going to have to deal with integrals that look like this: sines and cosines, products of sines and cosines where the angles aren't the same. And it turns out that in that scenario, the go-to trick would be something like the product to sum formulas. And basically, this is just a way that you can combine the addition formulas to rewrite products. So for example, we know that the sine of A plus B is equal to sine A cosine B plus sine B cosine A. And we know that the sine of A minus B is equal to sine A cosine B minus sine B cosine A. And so what you can actually do here is you can add these two, and you'd realize that you would end up with 1/2 sine A plus B plus sine A minus B is the same as sine A cosine B, right? And so if you're in a situation where you have like sine A cosine B, you can actually apply this. So this would mean, for example, that if I have sine of 3x cosine of 2x, I can actually write this as 1/2 of the sine of 3x plus 2x, which is 5x, plus the sine of 3x minus 2x, which is just x, right? And of course, integrating on the right is easier than integrating on the left. Product to sum form is not something that I would expect you guys to memorize, but I thought it would just be cool to show you. But this is an example of where integration by parts would not work. So there are times when you can have two of the same kind of function and integration by parts works. For example, you have a secant squared and a secant, integration by part works out. But then if I have a sine 3x times a sine cosine 2x, integration by parts doesn't work out. Integration has its nuances, what can I tell you? That's just par for the course. That's why I'm even having a section like this where I'm just talking about how to look at integrals, because you're surprised. You'll be in a situation where something completely reasonable just doesn't work out. And I just want you to be aware, how do you recover? How do you know what to try next? If your initial thought didn't work out, how do you finagle things, right? That's what we want to figure out here. Okay, so that is really integration by parts. So there are two main situations in which you want to use integration by parts. Assuming steps 1 through 3 didn't work, substitution is not going to work, basic rule is not going to work, you can't simplify to get a basic rule. The situations in which you would want to use integration by parts, if you have two different kinds of functions, or you have a function, but its derivative would have been nicer. Had I had the derivative of this function, it would be a lot nicer than having the function itself, right? Whenever you see something like that, then you're going to want to make that function the u and make the rest the dv, and chant it might work out. You never know, right? Yeah, you never know. You actually just try something. Step 5, and this one is pretty obvious, I think. It's techniques from trig integrals. So pretty much you have an integral where there's a bunch of trigonometry in it, and you're going to use trig identities to simplify, right? So if f of x dx is a trig integral, try to see if trig identities can help you simplify. Right, and that was something that we looked at, and we looked at several scenarios: cosine to the m of x times cosine to the n of x, etc. The important thing with the trig section that I told you guys is that the angles are actually always the same, right? So the angle is x in all of these scenarios, right? You didn't have a different angle, right? Because once you have different angles inside of the sine and cosine, it actually gets a lot trickier, like the example that I just did in the last one. Trig substitution. Now, it's very important, right? So a lot of times we hear trig substitution and students just focus too much on the trig. I do want you to be aware that trig substitution means you do not have trig functions to begin with, right? So if you see a trig function in your integral, it's not trig substitution, right? Because the trig is already there. Trig substitution is when you don't have trig functions, but you have a form that reminds you of a trig identity. So you introduce your own trig functions into the formula. So you use it when you see things like this, right? So it's useful when you have forms like this. Right? So you see like a variable squared minus a constant squared, or a constant squared minus a variable squared, or you have a variable squared plus a constant squared, right? Whenever you see expressions like that in your integral, that's when a trig substitution would be useful, right? But there should be no trig functions present to begin with. Okay, so that's that. Then you know, okay, trig substitution might be something I could do here. Another very important thing, sometimes students get really hung up on the fact that it has to look like x squared minus a squared. In fact, your x and your a are very fluid here. Like your x just means a variable part, right? So for example, these examples that I mentioned here actually do apply. So if you see something like 3x plus 1 all squared minus 5, this is actually of the form x squared minus a squared, right? Just because you don't literally have an x squared doesn't mean a trig sub won't work. So here, it's just like your x in the trig sub table is now 3x plus 1. It behaves like an x enough, right? So that's just a thing that you have to look out for. You might have to relax your ideas of what the x should be or what the a should be. Your a can be a radical, your a can be a fraction, it could be a decimal, it could be whatever. Your x can also be any linear function in general. It can also be a nonlinear function, but after a regular substitution, you realize that it ends up looking like an x squared minus a squared or u squared minus a squared or something like that. And that's when a trig substitution might be useful. Again, this is assuming that a regular substitution would not work, right? You don't want to use a trig sub when you don't have to, right? This was one of those techniques where, computationally speaking, it was just a lot of work, as you may recall, right? Next topic is, the next technique we learned was partial fractions. Now, partial fractions apply when you have a rational function. Rational function means rational function. This means ratio of polynomials. Okay, so when would partial fractions be a candidate? Well, of course, criteria 0 is that a regular substitution didn't work and all that. Okay, so when would I think of partial fractions? Well, 1, I have a rational function, which is a ratio of polynomials. 2, it is a proper rational function, which means that the highest power on the top is smaller, strictly smaller than the highest power on the bottom. And 3, the denominator has to factor. If the denominator doesn't factor, it's not going to work, right? So any of these, not having any of these 3 things means that partial fractions will not work. You have to have a ratio of polynomials, the denominator must factor, and the highest power on the top must be strictly smaller than the highest power on the bottom. Of course, if the function is not proper, you can use techniques to kind of finagle it. So we saw something like this earlier, where we could actually realize that this was, you know, x squared minus 1 plus 1. And so this would be 1 plus 1 over x squared minus 1 dx. And this part here is now proper. So partial fractions can work. So if it's not proper, that is the kind of thing that you can actually work your way around, right? So we saw that. If the denominator doesn't factor though, you can't really work your way around that. The denominator has to factor because the denominator factoring tells you how you're going to break up into smaller fractions, right? Same thing with this one. So here, you could just realize that this, here I can think of this as x squared plus 1 minus 1. And that's going to be 1 minus 1 over 1 plus x squared. And here you'd realize you don't even need a partial fractions. Okay. But just you trying to simplify to get into a situation where you could use the partial fractions means you ended up in a nicer situation at the end of the day anyway, right? So that is when you would do a partial fractions, all right? So you have a rational function. The highest power in the numerator is smaller than the highest power in the denominator. If not, I can do like a long division to make it so. And the denominator must factor. So in this situation, assuming that a regular substitution and all that other stuff didn't work, partial fractions would be a nice thing to try. And I would actually apply a partial fractions before I apply something like a trig substitution. You'd realize here, like in the x squared over 1 plus x squared, technically you could do a trig sub here, x equals tangent theta. You'd work harder than you have to though. And in the first situation, a trig sub could also work, x equals secant theta. You'd work harder than you have to though. So I probably wouldn't actually do that. Partial fractions is probably the preferred technique for these guys. And you would have to finagle them so that it can work. Lastly, we saw the Weierstrass substitution. So this is when you actually have a rational trig function. So it's like a rational function, but instead of just an x, you have like a trig function there. So instead of where you see x, you have a sine x or a cosine x or something else. So it's a rational trig function, okay? And your trig identities don't help. So in the first scenario in here, trig identities actually help. So I would do something like a 1 plus sine x. I would actually multiply by like a 1 minus sine x over a 1 minus sine x. That would turn the denominator into a cosine squared. And then this guy would actually break up into a secant squared. And this into a sine x over cosine squared. And for this one, that's just a tangent. And for this one, you can do a u equals cosine, right? And you would end up with something like a plus 1 over cosine, right? So trig identities actually help you in the first one. So, so I would not use Weierstrass here. Right, because something simpler worked out, just a nice trig identity, 1 minus sine squared equals cosine squared. So I see the 1 plus sine squared, and I know the difference of squares formula very well. So I realize that if I multiply by 1 minus sine squared, the product is going to be 1 minus, if I multiply by 1 minus sine, the product is going to be 1 minus sine squared, which simplifies to a cosine squared. So that would work out. Trig identities would not help here. However, it's a rational trig function, so maybe trying something like a Weierstrass would work. And this particular example we've actually done in class, so I'm not actually going to do that again because it actually takes a while. Okay, so that's where when you would actually use a Weierstrass, right? So just to recap from that is the last technique we did. I don't think I have anything else to say on that. Oh, there's an example I do want to go through afterwards. Okay, so just to recap, right? So overall, this is the general approach, and I think it works very well for calculus 2. You see a random integral that you need to compute for whatever reason. The first thing you're going to think, is it a basic rule, right? Is there just something that I have memorized that it fits so nicely with this thing, I can just apply it and move on with my life, right? Second thing you check, can I simplify it to look like a basic rule? Can I divide into each part? Can I apply some identity? Can I do something to finagle it to look like a basic rule? And if so, that's what you should do. The third thing is, would a substitution work? right? You always try to get a substitution to work. It's not always going to be obvious in the beginning when the substitution would work. How you just assess something for a substitution is to just look, what is making this thing complicated? What is making it not behave like a basic rule? Replace that thing with a single variable and see how it looks, see how it works out, right? So the radical x in the power of e to the radical x makes it complicated. So replace the radical x with a single variable, see what happens, right? Replace the radical of 1 minus x squared with a single variable, see what happens. Replace the radical of 1 plus x squared with a single variable, see what happens, right? Sound like a Trump here. Oh, we'll see what happens. Okay, right? But you try the substitution. Try to get it to actually work. Move things around. See, can I get my dx out of this? Try to get the substitution to work. If it can work, it shouldn't be too algebraically difficult to figure that out. But you do have to consider it. It's not always going to be obvious. In Calculus 1, it was always obvious when integration by substitution would work because literally at that point you had no other technique. So, but in Calc 2, it's not always obvious. You should always try, always consider a substitution. Assuming none of that works out, integration by parts, when would you do that? If I have two different classes of functions, or I'd rather have the derivative of what I'm looking at as opposed to the thing itself, right? That's basically when integration by parts is going to sometimes work out. Then what about trig techniques? Well, it's just like, okay, if I have a bunch of trig functions, will applying some trig identity help make things nicer, right? So that's basically kind of like a simplification, step 2, but applied to trig functions. Trig substitution, you do not have trig functions in the beginning. However, you see these very nice forms, x squared minus a squared, or x squared plus a squared, or a squared minus x squared. And they might be hidden under some radical or a cube root or whatever, but they're there and you can actually take advantage of them, right? And you should just remember, it doesn't have to be literally an x and literally a nice constant number. A can be pi, it can be a half, it can be radical 2, it can be whatever. It just has to be a constant that you can think of as a square. Moving on to partial fractions. Why would you do partial fractions? So ratio of polynomials, the denominator factors, and it's proper. If it's not proper, but everything else works out, I can actually do long division or manipulate it algebraically to get it to work out. And the Weierstrass, meaning you start out with trig functions. In fact, it looks like a rational function. However, instead of a variable, you have a trig function in place of the variables. And your trig identities didn't work, so you might try a Weierstrass substitution. And we know how to get that to work. So those are the techniques. Let's go with an example from the trenches here. So this is an example that a student asked me about. And I figured in this past week, I figured we can actually apply what we've learned so far and kind of get around doing this. So let's suppose that you saw this as an integral. What would you do? I've been talking for a long time, so let's see you guys start chiming in here.
I'm not sure if the bottom is factorable.
Well, it's a monic quadratic. So can you think of two numbers that when you multiply, you get a positive 1, and when you add them, you get a positive 1?
1? Oh, wait, no. Never
Yeah,
mind.
yeah, it's not going to work, right? So it'll have to be like, it's either 1 and 1 or -1 and -1. And for both of those, if you add them together, you don't get +1. So the denominator does not factor. Huh?
I think you could complete the square in the denominator.
Okay. So the first thing you would check, did you actually think about a substitution or no?
I did, but then I figured that I couldn't factor the denominator, I didn't think, so I wasn't sure how a substitution would work.
If you were to try a substitution, what would you try?
I would have tried u equals the denominator.
And why would that not work out? I mean, you could factor out a 2. and then you would get x plus a half.
And then you could like add and subtract 2.5 on the numerator.
Okay, so you would add a half and subtract a half, right? So minus 2 minus a half, that's what, minus 5 over 2?
Yeah. But then also you have to add it.
I did. I added and subtracted.
Oh, okay.
Right, so I added a half and then I subtracted a half. So if I take minus 2 minus a half, I get minus 5 over 2.
Okay.
Right? And so now you realize, okay, so I can break this integral up into 2 parts. And substitution works here, right? Okay, now, so I know I can get the other one to work. In fact, that's going to be straight up like an ln of x squared plus x plus 1. Now, what about this part? Okay, so you're always trying to get the substitution to work. And sometimes it might not even work fully, but just isolate the part where the substitution is going to work. You will have something smaller left over to deal with. And so then you try to figure out that part. So now we're in this part, and I know this is the part that a substitution is not going to work. So now I'm not thinking substitution. Because like, if I could have gotten a substitution to work, I would have gotten it to work with the other part already. So now is when I would start to worry about, okay, does the denominator factor? So here you'll notice that denominator does not factor. Okay, so knowing that it does not factor, what would you do?
For the left side, or the right side? The left side, right?
Come again?
Like we're talking about the left side, right?
No, the right side. The left side is done. Like the left side, we have that solved. That's ln of x squared plus x plus 1. Right, there's nothing else to do there. That's a substitution. 1/2. Right? So now we're focusing on the right side. So based on what I've told you so far in this lecture, how would you actually work that out?
Would that be a trig substitution?
How would you get that to work?
Well, I don't like the extra x in the middle there.
Okay. So what can you do about that?
I have no idea.
Would you?
So the denominator doesn't factor, and you see a quadratic. So what else could you do with it?
Complete the square.
You can complete the square. That would make it look like a form that you could do a trig sub with, right? So if you were to complete the square here, that would look like what? X plus a half. And that would be, you'd have like minus a quarter, and then you add 1. So that's like 3 over 4. Right, that's going to be the complete square. Okay, and now what? So now we're focused on that.
Can you do the like 1 over a inverse tangent of that like x plus 1/2 over a?
Yes. So yeah, so once you get this new integral, you go over everything again, right? So at first, what I would do is substitution, and not completely necessary, but I think it's actually safer at this point because you might have this constant factor that you have to multiply. You can substitute like u equals x plus 1/2, right? And you are going to get and yeah, at this point, you know that's a basic rule. So you don't even need, I mean, in the beginning, we thought we'd need a trig sub, but after doing this kind of simplifying along the way, you realize you actually don't need a trig sub. This is a basic rule. We do know that the integral of 1 over x squared plus a squared is 1 over a tan inverse of x over a plus c, right? Where here, our a is equal to radical 3 over 2, right? And so this guy would become, well, minus 5 over 2 times 1 over a tan inverse of x over a. And I'll use the x plus 1/2. So this just becomes minus 5 over rad 3 tan inverse of 2 times x plus 1/2 over rad 3 plus c. I can even simplify that a little bit more. So that's minus 5 over rad 3 tan inverse of 2x plus 1 all over rad 3. And then this guy comes all the way down. And we have a 1/2 ln of x squared plus x plus 1. Okay. So, I mean, it takes practice to see all this stuff, but if you follow the guidelines that I gave you in this lecture, you'll start to see things like this a lot easier. And then with practice, it becomes very natural to start to do all these things. And this is a very common type of integral. I'm pretty sure that you'd have seen similar examples on your homework at this point. And you'd realize that the amount of strategies that you'd have to know for this class, at the end of the day, it's really not a lot. If you see one strategy work, you'll start to notice other situations in which that same kind of strategy would work. So yeah, so that's how you would actually deal with that integral. That's, believe it or not, one of the easiest ways to actually approach this integral. There are other things that we could have done. We could have completed the square right from the beginning and hit it with a trig sub. I think it'll actually be a little bit harder to actually get that to work in general, but you could have done that as well. However, by trying to get a substitution or a basic rule in play before worrying about something like a trig sub, you realize that you kind of see this thing kind of fall in your lap already. So that's nice. Okay. So what I want to do for 5 minutes is to put this into practice even in a nicer way. That's going to be fun, at least for me. I don't know about you guys. So one of the ways in which I got good at integrals, and I can speak for some of my friends as well, back when I was a little Jhevon and I was in Calc 2, is there's only so many problems you can practice in a day, right? It seems like, you know, you do a lot of integrals, but then you get on the quiz and then that one integral stumped me. After I did like 50 integrals this week, and then I just never saw something like this, right? So there's always a balance between how can I practice enough problems to know how to deal with any scenario, right? Because it does take some sort of skill and experience. But if you were to actually have to think through every problem and write it out like this, it actually takes a lot more time. So what you want to do is you want to do enough problems so you kind of feel the ropes, but then how you can practice after that to kind of multiply your efforts in a nice way is that eventually you want to get to a point where you can actually mentally kind of work through a problem. And I don't mean actually come up with the exact answer, but I mean to kind of come up with, this is a strategy that I would have hit this problem with, right? So, believe it or not, at this point, it might seem strange to you. However, you can get to a point where when you see this integral, you would actually know that this is what would happen without actually specifically doing it. Like you would actually look at this integral and be able to see, oh, well, a substitution isn't quite going to work on everything. However, I can split it into two parts. Substitution is going to work for half of it. And then the other part is going to be maybe a trig sub after I complete the square, but probably a tan inverse formula. Like you can actually look at this and you can tell someone, okay, here's what I would try first, second, third, and I would know what would happen, right? And you can kind of like mentally do this practice. Like when you see an integral, just practice being surprised by an integral and then coming up with a strategy on the spot. And the goal would be to actually get to a point where you can do this relatively quickly for any random integral. So you want to challenge yourself to maybe do this like within 5 seconds or something like that, which I know might sound crazy at this point, but I promise you it is doable. Little Jhevon, who wasn't the sharpest tool in the tool shed, actually managed this along with a lot of people I knew. And it's a very good strategy. You kind of make a game of it. Maybe you can actually find someone else in the class who you're in a study group with, and you can like challenge them, you know, like, okay, if you give me 10 random integrals, and if I tell you the proper strategy within 50 seconds, then you buy me lunch. If not, I buy you lunch, right? You make it a little fun. You put a little nice wager on it. You make it a game. You make it a little fun. So you can do that. So what I want to do with you guys for a few minutes is pretty much that. I'm going to play an integral game with you guys, right? So these are the rules. I'm going to show you a bunch of random integrals. And you guys, you're not going to tell me the exact answer. We're not going to work it out exactly. You are just going to tell me what you would think, how you would attack that integral, what strategy do you believe would work, and we're going to move on. The rules are also, you have to be somewhat specific. So if I show you a random integral, you can't just say substitution, because you could be guessing, right? Like you would have to say something like, I'd substitute x squared plus 4, right? So you have to have some sort of specificity to it. So I know that you're not just randomly guessing, right? So those are the rules. I will show you a random integral. And because this is our first time, I'll give you guys like 5 seconds to come up with a strategy. And you're just going to chime in and tell me the strategy. So you can have your mics off, everyone. I don't know if there's going to be like a bunch of people tripping over each other to answer, but we'll see how that works. So everyone can take their mic off. And then I'm going to show you an integral. And the goal is to, as quick as possible, just try to tell me what strategy would work. Okay? Do we get the goal, the rules? Okay. So, all right. You guys ready? We're going to start. We're going to just do this for a couple minutes, not very long, just as practice. Okay. Let's go. Okay, so there are a bunch of problems here, and I will leave these in the PDF of the notes, of course. So I copied the problem sections, the integral review sections from a bunch of different textbooks, including your own textbook, and we're just going to actually look through these. Okay, all right, 11.
Substitute u equals x squared minus
X squared minus 1. It would work. It sounds, I would fix it a little bit though.
Sorry, u squared equals x
U
squared
squared equals x squared minus 1 is actually
minus
better.
1.
Okay, see, that wasn't so bad. You guys saw that in like a few seconds, right? That was good, right? Now, when you get good enough, you can count that as I've practiced an integral, even though you've literally spent 3 seconds, right? You can take 5 minutes and practice 30 integrals, right? As opposed to actually going through something. But you'll know that you're right. You look at it and you'll know, yeah, definitely, that's gonna work. I've seen that strategy over and over. Okay, so that one done. What about 7?
U substitution, U equals ln of t.
Yes. 6.
Integration by
Integration by
parts.
Integration by
parts.
parts.
You have to be more specific.
U is ln x, du is, sorry, U is the x to the 5th. dv would be ln x.
No, other way around.
Other way.
Liate,
U is
right?
ln x dv.
Okay. So I'll give you guys that. You kind of stumbled there in the last bit. How would you integrate that?
U sub.
Partial fractions.
No. Substitution, or even nicer, U equals 2x plus 1. What about this?
Integration by parts.
Partial fractions.
What are the parts?
And then do partial fractions.
What are the parts?
Well, secant tangent's a derivative, so we can make that dv, and I would make u just x. Sorry, other way around again.
What? Your U would
Well,
be
I
who?
want- my dv is secant x tangent x, and my u is x.
Okay, that'll work. Okay. Bum 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 bum. This.
Substitution, u equals 1 plus square root x.
Yes, you can get that to work out. Bum 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 bum. This.
What the hell?
Okay, time's up. Okay, what
For
about this
burning,
one?
You don't do that one.
Substitute u equals 1 over x.
What's gonna happen if you do that? Something's gonna happen where you're gonna need a second technique. Does anyone see it? No. Okay. So yes, you would start out with a substitution of 1 over x. You're going to realize you're going to end up in a situation where you're going to need an integration by parts. You're going to end up with a u cosine u kind of situation. Do you guys see where that would come from though?
No.
Because once you have the u equals 1 over x, your du is going to be minus 1 over x squared, but you have an x cubed in the denominator. So you're going to be left over with a 1 over x. That 1 over x is going to be the original u that you substituted. So you're going to have that u cosine u, right? With a negative sign, right?
Okay.
So how would you use this?
You can multiply, like manipulation. So you can multiply 1 minus cosine over 1 minus cosine. And
Okay.
the denominator would be cosine squared.
Yes, that's good enough. How would you do 55? Okay, time's out. You're taking too long.
Substitution, but I don't know what.
Substitute, but I don't know what. Where else? How would you do this? 60.
Partial fractions.
No, it's a radical. You can't have the partial fractions. It has to be rational. Okay, what about 59?
Partial fractions.
Partial fractions. So you can factor that by looking at it as the difference of squares. You can keep breaking it down. Eventually, anything you can see that might happen? Anything that you notice is going to pop up eventually?
We'll have
An
x squared
arctan
plus-
is going to come up somehow, right? Hopefully, I don't know if you saw that. Like once you start doing the partial fractions, you're going to get an x squared plus 4. And that's going to be one of those 1 over x to the x squared plus a squared kind of thing. Okay. What about 16 here?
Save a secant squared and then turn them into tangents and make u your tangent.
Yep. $33.
Trig substitution. of 9 minus x squared?
No, you can do u squared.
You can do a u squared substitution, 9 minus x squared. If you were to do a trig substitution, what would it be?
Oh, the a squared
minus
minus
x squared is sine.
So x is what?
sine squared.
No.
3 sine theta.
X would be 3 sine theta if you're doing a substitution here, a trig sub. However, that would be a lot harder than a regular substitution would work. How did you know a regular substitution would work? Whoever said substitution.
Because the exponent of the numerator is odd.
Right. So that's a dead giveaway. So this is a regular substitution. It would be a trig substitution if it were like an x squared over this, right? Okay. So we'll stop there. See, look at that. We did how many integrals did we just do? Well, we got
Too
a
many.
few wrong. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, and we did that in what, 5 minutes? Right? You think you can actually write out a solution to 10 integrals in 5 minutes? No, right? But you saw how that practice would actually be beneficial, right? Like you can know, okay, all right, I see how, yeah, right? So you can actually do that, right? So you can literally like practice over a weekend, practice hundreds of integrals, and you'd actually get good at that. Maybe one day I'll tell you a story about that, because I actually have a story about practicing hundreds of problems over a weekend and the results of it, but maybe I'll get to that. But yeah, actually overall, you guys actually did pretty well. I did this experiment a few times in the classes. It was like, usually it ends up a disaster, but you guys had some good, you guys are all right. Okay, great, awesome. This is good. But that's just something that you can do with yourself. Get like a massive integration problems, right? Like hundreds and hundreds. And you just, after you do the homework, after you have the strategy down, just go through. Could I actually think through how to actually do these, right? And it's just like extra practice, which is really nice. And practice, it makes you practice seeing the strategy of how you would actually approach something, which is actually pretty good. In some sense, it's actually the hardest part, right? To actually figure out how I would go about approaching this random integral. How do you approach 3? You guys are taking too
Do
long.
a substitution.
All right, substitute equals cosine. Okay. All right, so that's that. I'll leave these guys here for you to actually get some more practice on. But yeah, that's the last thing. And if you find yourself being stumped with a problem, that's a sign that maybe I don't know this strategy as much as I should. So the first thing I would actually do is recommend that you actually, the strategy that I wrote down, write it down more concisely somewhere in your notes, and then actually try to apply that strategy. Apply the strategies to a bunch of different problems. And every time you're doing homework with a bunch of integrals, you try to apply the strategies. So you get to a point where you're kind of used to, okay, I know in this kind of situation, this strategy would tend to work out. And then once you kind of have that under your belt, then you can get extra volume of practice in just by doing this, maybe even challenging other people to it. So but what you can do is like problems that you've actually solved, you can challenge someone else to do those. So you actually saw what the full working out is, and you can actually challenge someone else and see if they actually get it. Within a few seconds, they can actually tell you. And practice being able to do this, like I said, in a few seconds. Also practice being able to do this where you're seeing like a couple levels ahead, where you can see that, yeah, I would start out with a substitution, but then I would get to a point where there would be an integration by parts. Or I'd start out with a partial fraction, but then I'm gonna have to do that arctan formula, right? Eventually you'll be able to see this, right? And at this point, like when I do these guys, I pick this at random. So I'm doing this along with you guys. And so when I'm telling you what I'm seeing is like, I'm also doing it right on the spot. Every time I pick a different problem, I think. Okay, so that ends up with the integration strategy, which took a little bit longer than I expected, but I think it was worth it. Okay, Maybe, oh, I see a chat here. Huh, sounds like so much fun. I don't know if there's sarcasm in that, but I'll pretend there's not. It wasn't. Yeah, this game sounds fun. God, Jhevon is such a, okay. I can introduce the concept of the next topic, although we won't really do much in the next 3 to 5 minutes. Okay, so the next topic that I want to cover is actually something called improper integrals. So technically in the book, it's not the very next section, but I'd want to cover this before I cover the section 7.7. So we're going to skip 7.6 because that's about, I think, using a calculator to do integrals, which we're not doing. 7.7 is on numerical integration, which I want to do after this, improper integrals. So improper integrals, you're going to have to apply all you know about actually doing integrals anyway. So it's just a nice segue. Improper integrals only applies to definite integrals, but definite integrals in a certain scenario. Okay, so you might have recalled from Calculus 1, you learned something very important called the fundamental theorem of calculus, which you probably won't realize why it's so fundamental until the end of Multi-2, but I digress. It's a very fundamental theorem, very important theorem. One thing you might not have paid much attention to is that the fundamental theorem worked as it worked in Calc 1, we assumed certain things about the function. One, we assumed the function was continuous. Remember when we were proving the fundamental theorem of calculus, we used the mean value theorem in the proof, and the mean value theorem required that we were continuous on a closed interval. We also assumed that the interval was of finite length. Again, we have to think of it as a closed integral. A and B are some finite real numbers. An improper integral is what results when one or both of these conditions are no longer true. So that leads us to this definition right here, right? An integral from a to b of f of x dx is called improper. It's an improper integral if, that should not be, I think that. Let me actually fix that one.
Can you scroll up a little bit? Perfect, thank you.
Right, so the fundamental theorem of calculus assumes that our function was continuous and the interval was of finite length. So you might be wondering, well, what if this didn't happen? So that's what an improper integral is. And I mean, there's some more to say about the discontinuity, but the type of discontinuity, like if you only have discontinuity at an isolated point, it actually doesn't affect the fundamental theorem of calculus because you can actually break up into intervals and you'll actually get the answer to work out, but I digress. So the discontinuities that we really care about are the ones like infinite discontinuities. If your function shoots up at a vertical asymptote or something like that, that's actually a big deal. The fundamental theorem of calculus can actually deal with that very well. So if you have a definite integral where one, f is discontinuous at one or more points on the interval a, b, or the lower limit is minus infinity, or the upper limit is positive infinity, you get what's called an improper integral. Okay, so we will call the points of discontinuity or minus infinity or infinity, I'm going to call them bad points, right? Because there are points that won't work in the fundamental theorem of calculus. They're not really, that's not a technical term, that's just a term that I call it. So just to introduce the idea of how you'd approach such an integral, I'm going to call it bad points. Okay, so how do you deal with improper integrals? Okay, so one, you're going to identify the bad points. So if your lower limit is minus infinity, that's a bad point. If your upper limit is infinity, that's a bad point. But also, any point between the interval that makes your function discontinuous is also a bad point. So you have to identify these bad points. What you're going to then want to do is you're going to want to break the integral up into pieces, sort of like how you learned in Calc 1 as well. Integral from a to b is the same as integral from a to c plus the integral from c to b, right? So you can break up the integral so that you expose these bad points such that only one bad point per integral would be there. Then what you're going to do is you're going to take limits to approach the bad points. Because I can't actually plug the bad point into the integral, what I do is I take a limit to approach that point and see what happens. What you're then going to do is you're going to compute all the limits. if they add up to a finite number that makes sense, we say that the integral will converge to that number. And if the limits don't add up to some finite real number, then we say the integral diverges, kind of because the limit diverges, okay? And that's basically it. So here's a summary, which you can take a picture of. And then I'll actually do a couple quick examples where I actually break this up, and then I'll let you guys go. Shouldn't take too long. Okay, so you start by identifying the bad points. You're going to break up the integral so that, and this is actually important, one bad point is exposed per integral. That's very important. Step 3 is you're going to take limits to approach these bad points. Do the integral as normal, but you take limits to approach them, and you'll see what that is like next time. And then you compute the limits. Let's actually make steps 1 and 2 is what we're going to focus on for the next 2 minutes. Okay, so here is an example of an integral. The integral from 1 to infinity of 1 over x, right? So this is like basically what we're doing here is we're taking the graph of 1 over x, and we want to find the area under the curve from 1 to infinity, right? Which at first sounds very crazy, like isn't the area going to be infinity? Not always. We'll talk about this next time. But at this point, don't worry about what the integral is going to be. I just want you to identify what the bad points are and then break it up. So what would you say the bad points are for this guy?
Just the infinity.
Just the infinity, right? Which we can say b equals infinity. So there's nothing really to break up, so don't need to break up. Because there's only one bad point, and he's already exposed. What you would do, though, is you would do something like the following. You take the limit as n approaches infinity of 1 up to n of 1 over x dx. And you would actually compute this integral as you would normally with an n as the upper limit. You would get an answer with n in there, and then you take the limit. But again, we'll do that next time. What about this one, 1 over x squared? What are the bad points?
Would 0 count as a bad point?
0 would count as a bad point. So 0 is on the interval we're considering. So yeah, the negative infinity is a bad point. The positive infinity is a bad point, and x equals 0 is a bad point. So there are 3 bad points, which means I would want to actually break this integral up. How can we break this up? Well, I can break it up into negative infinity to 0 plus 0 to infinity. Is this good enough?
Don't those still have 2 bad points in them, though?
Right. So this is actually not good enough because there are 2 bad points. Notice that the infinity and the 0. So you only need 1 bad point. So you'd actually have to break this up further. So what you would actually do is you'd pick an interim point, say minus infinity to minus 1, for example. Then minus 1 to 0. Then 0 to 1, let's say. It actually doesn't matter what interim point you pick. Plus 1 to infinity. So notice here, I have 1 bad point on each integral, right? So it's very important that you first identify the bad points, and then you're going to split your integral into pieces, because we're going to approach these points with limits, and we can't approach with a double limit. Like I couldn't take a limit approaching infinity simultaneously approaching 0. So I have to kind of break these guys up, right? Now, once you actually do that, you can actually start putting in limits into these things. And I'll let you go. I'll leave the examples here for you guys to try for next time. But just to kind of show you where we would actually go with this, I would have a limit approaching the negative infinity. You'd actually take a whole other limit. So let's say m approaches 0. And technically here you'd be approaching 0 from the left. Here I can say the limit as p approaches 0 from the right. And here I would say a limit of, let's say, q approaches infinity of that. And you would actually compute each of these individually, right? So I know that the integral of this is going to be minus 1 over x between n and minus 1. And then I would plug in a minus 1 and then plug in an n. And then I let the limit as n approaches infinity. And of course, that part is going to go to, what would that limit go to?
1.
1, right? And you would literally do this for each part. If each part adds up to a number, then you can just add these numbers, and that's what your integral converges to. If any of these integrals mess up, then you say the integral diverges. So one of these guys might go to infinity, for example, which you'll notice that these guys, the guy in the middle is going to go to infinity. So it'll actually mean that this integral diverges. The area goes to infinity. We'll do that next time. In the meantime, I would just rather you practice actually breaking up the integrals so that you get one point exposed. So I have a couple more examples left over here for you to actually try doing that with. And then at the end, if you want, you can do some full-fledged improper integral examples here. But we'll wrap up there for now. And yeah, we will stop there. Okay, so with that, we are going to wrap up. Yeah, so I just started off into improper integrals. I will leave this in the notes for you to actually try some of the problems, but we'll finish this up next time. That being said, yeah, I think that's all I have for you today. So thank you for your attention, and I suppose that's it. So.
Thank you.
Good night, everyone.
Thank you.
Have a good night, and I will see you guys in the next one. Ciao.